All right, hello, welcome back. I'm going to be talking to you in this video about some solutions to second order differential equations. Really, I know I try to keep this class to techniques that we use to solve, but there's a couple of things, a couple of nuts and bolts I'm going to need to tell you about to support, our learning about solutions and our moving forward and, solving the second order ODE homogeneous equation with constant coefficients where it doesn't come back super nicely like we did in the last video. So maybe if I said in the next video I'm going to show you about that, that might have been a lie because I need to tell you a couple of things first. Okay, so again, just to remind you, I'm talking about a linear second order ordinary differential equation. So that's going to be a differential equation of the form y double prime plus p of t y prime plus q of t y is equal to g of t. Now, for most of our discussion of second order differential equations, we're going to be interested in where g of t is equal to 0, and that's what we would call a homogeneous second order differential equation. And it's linear because, well, it's p of t times y prime and p of t times y. We're not seeing y squared, we're not seeing sine of y, nothing like that. Okay, so now the first thing I need to tell you, which is the kind of the existence and uniqueness theorem for second order differential equations, is that for this given differential equation, for the linear second order, kind of that form with, let's say, y of a is equal to y0, and y prime of a is y prime 0. Okay, so basically if we got, if it comes with an initial condition and we're looking at this, this will have a unique solution provided that p, q, and g are continuous, right? And so it'll have a unique solution on a given interval that contains this point A, provided that on that same interval, p, q, and g are all continuous. And I'll work through an example for you just to show you what I'm talking about. We'll have a unique solution on an interval I with a being an element of I, provided p, q, and g are continuous on that interval. Okay, this is not going to be the most important for us in this class. This is important in general, and of course, unfortunately, the proof of this theorem is kind of laughably beyond where we are right now, so we're just going to take this one on faith. Okay, but let me kind of just show you a situation. Let's see, what example did I set? So y double prime multiplied by t plus 2. Let's grab this. Plus ty prime plus cotangent of ty is equal to t squared plus 1. Okay. And we know that, what would I say, y of negative 3 is 11. Not sure why. My 11. And y prime of negative 3 is equal to, I don't know, maybe something like 2. Okay. And we want to know, kind of what is the interval on which there is going to be a solution to this differential equation. Okay. So what I need to do is I need to get it written like this. So I need to divide away whatever's attached to the y double prime, right? Okay, so y double prime plus t over t plus 2 y prime, what is it? Plus cotangent is cosine over sine. So that's cosine t over t plus 2 sine t y is equal to t squared plus 1 over t plus 2. Okay, This has discontinuities at t equals -2 and at really any place where sine is 0, so that would be 0, pi, 2 pi, 3 pi, and -pi, -2 pi, -3 pi, -4 pi, -n pi. All right, so really what I've got here is I'm going to kind of just mark off my, my points of discontinuity. Obviously -2, that's going to be troublesome. I'm going to have 0, I'm going to have pi, and I'm going to have 2 pi, and so I would have -pi here, and maybe -2 pi, just to give you a picture. And then the initial condition they gave me was y of -3 is 11, so I'm in here. Okay, and if these are kind of my points of discontinuity, this is going to be the interval on which I'm guaranteed a unique solution. Okay, so this one will have a solution on and it's a unique solution on the interval -pi to -2. Okay, that's about all you need to know about the existence and uniqueness theorems at this point. And let me tell you something else about solutions, specifically solutions to a homogeneous second-order differential equation. All right, so next I need to tell you, if we're talking about a homogeneous differential equation, second-order linear, like this, and I've got two solutions, then any linear combination of these will also be a solution. And I think what I want to do, I think I will go through this, because it's really not that hard. It's really not going to be that hard to show. It just is using the linearity of the derivative. Hold on, let me think. Do I really want to get into this? I think maybe I won't. And I'll tell you that if you plug in y1, right, into this, and we take this, and g of t is 0, well, I'll get back 0. And if I were to put y1 plus y2, well, I'd have them separately, I'd have 0 and 0, right? And I could add those together, and that would be 0 again. Then if I had c1y1 plus c2y2, well, it would just be some multiple of 0 plus another multiple of 0 is still going to be 0 there, and it will satisfy the differential equation. I think that, well, it's the same thought as the one in the last video, the constant coefficient second order ODE. So then c1y1 plus c2y2 is also a solution. Yeah, I think that should be pretty evident. I don't think I need to go in and prove that for you. But before I do move on, I want to point out something that this C1 and C2, these are constants. I am not necessarily demanding that they be real numbers. In fact, I need them to be able to be something besides real numbers, you know, here, maybe the video after next. Okay, so I'm just going to say that these are constants. And now I'm going to tell you about another theorem. Okay, and this one is going to kind of go a little unjustified, but I think you have seen evidence of this in the last video. So if we have two solutions that are what we would call linear independent, and by linear independent, I mean pretty much the same thing I meant in linear algebra. Okay, y1 and y2 are going to be linear independent if they are not just a multiple of each other, a scalar multiple of each other, a constant multiple of each other. Probably a more rigorous way of saying that is that the only way that we can add y1 and y2 together to get 0 is by taking 0 of each of them. Okay, the only linear combination of y1 and y2 that I can take to get a constantly 0 function would be 0 of each. Okay. So they are linearly independent solutions. Then that's going to give us that the general solution is kind of just is the general linear combination of them. Then the general solution is going to be is C1y1 plus C2y2. Okay. So, and pretty much this is the fact that it's a second order differential equation. There can be at most two linear independent solutions, and that they will pretty much span the entire general solution, to use language from linear algebra. Okay, and what else did I need to tell you? Feel like there was something else that I was going to throw in, but if there's anything that just kind of is so urgent, I'll just tell you in the next video.